So let's go back to what we were working on last week, which is calculating probabilities from population data sets. So if we have the population data set here, we saw that we can calculate probabilities just by counting how many times something happens. So here I'm using the count function. I'm just counting how many times this particular condition is met. And then my probability is the total number of times that happens divided by the total number of people in my population. So that's what's implemented here, and we talked about this code before. So this is a probability of a particular event happening. You see, this is the output that I get. So this thing in this population, 80% of the people are between 2 and 4 years old, inclusive. Okay, great. Now, what I'm going to tell you is that I can get such probabilities, any probability really, I can get just from knowing the density function. So I don't need the whole population data set. I only need the density. This is kind of the point of density is that I've boiled down this very complicated, 5 million population, 5 million row population into something that is, in this case, really just 5 numbers, or rather a function that takes values on five numbers. So how do I calculate that probability if I just know the corresponding density? So I've told you already how I could calculate this density from a population data set. Now how do I calculate the probability from a density? So the probability of interest is the probability that somebody is between 2 and 4 years old, in this case, which corresponds to these inputs and these values of the density. So in fact, to get this probability, all I need to do is add together the values of the density functions at the relevant inputs, which are 2, 3, and 4. Again, if you want to do this concretely, you can do it with the population data set. You could also, here I'm just basically comparing, right? So with the population data set, remember the answer we got was 0.8. If I add 2, 3, and 3, what do you get? 8. So you see it matches exactly. And that's not coincidence. It's basically just because by adding the values in the density, we've just counted rows in the population. We've just counted them kind of in a different way. So when you see, so this is the generic, or this is the particular thing that we are looking at, the probability that x is between 2 and 4. And we're saying this is the sum of the densities at each of the values that x takes. More generically, you may see stuff that looks like this. So you still have probability of something, but what is that something? We often say x, this is our random variable like age, and then this little guy means in, and here on the right-hand side, you'll see some set. So this is very generic notation. Concretely, I could rewrite this as x in 2, 3, 4, meaning that x takes one of these values, I don't care which. Again, this is just a little bit of notation so you recognize it. So usually people write sets like that as like capital letters, like in fancy script, sometimes not. This little in guy, this comes from est, which you may know in Latin means is. And that's because you would write, like, for example, if this represented the set of all apples, you could write like and x is my apple. You could say my apple is an apple, right? Or you might say here script x is the ages between 2 and 4. So you might write an age between 2 and 4. You might say, 3 is an age between 2 and 4. So this little guy here, basically people were abbreviating this with like Greek E, and then eventually people just started writing it like that, and that's where we get that. So again, like it's all notation, it's all made up. It's you just kind of got to know what's what. So generically, when we ask about the probability. So again, this is like a concrete example, but the general case will be we're asking about the probability that a random variable takes some value in some set. right? So it could be x is greater than 4. It could be x is 4 is an even number. So it doesn't matter what the set is. If we were to calculate the probability that x is in that set, we know we would just count how many times that happens in the population. But if what we have is not the population data set, what we have is the density, how do we generalize this kind of formula here? And the answer is you just have to add up the values of the density at all of the values that are within that set. So if script x were all even numbers, then we would add up the values of the density at all even numbers. Okay, and notationally, the way that is sometimes written is, I think we saw the big sigma, which just means sum over. So it says add up this, looping over the values little x in x. So for example, if script x were values 2, 3, and 4, we would be looping over those values. So first we would get f of 2, which is here, then add that to the next value, f of 3, and then add that to f of 4, and we would be done. But depending on what's in script x, we'll have a different number of terms. So that's just explaining what this little notation means. That's the formula version, but again, the conceptual idea is really quite simple, and it's that, so here's a concrete example, x greater than 2. So we're just adding up the values of the density at all values greater than 2. The conceptual idea is quite simple, which is that here's the population data set, again, artificially very small, just so that you can see what's going on. What we're doing is counting up how many times this value is greater than or equal to 2. So here it's 1, 2, 3, 4. So it's 1. This instance gives me 1/6, one time. This instance gives me another time, another time, another time. I add up 1 plus 1 plus 1 plus 1. I divide the total by 6, right? All I've done when I compute the density is that I've grouped the values of 2, so this value and this value, into one bin. So I've already added 1 plus 1 is 2. The values of 3, I group all those together. There's only one of them, so that's a 1. And the value of 4 gets a 1. And then all I'm doing is adding these numbers together. So it's 2 plus 1 plus 1, which is 4. But that's the same as 1 plus 1 plus 1 plus 1, right? So literally all I'm doing is grouping the similar values and then adding those sums instead of just summing everything kind of in a flat format. That's it. So that is conceptually what this formula means. That's the kind of the thing to understand and remember, not necessarily the symbols, although you're going to have to recognize the symbols at some time or another, so it's good to know them. But conceptually, all you're doing is adding or counting. You're just you're counting in groups. So I spent some time making these slides, and at some point I've been using ChatGPT for a lot of stuff and kind of testing out how it works. So I said, hey, maybe instead of kind of making this and drawing arrows and numbers and stuff like that, I was like, I wonder what ChatGPT will do if I just asked it to make me a graphic illustrating this concept, right? That the probability that x takes some value in a set is really just the sum of the density looping over the values in that set, right? Where this thing is the mass function or density. I just want to show that the former is counting the population, the latter is just adding up subsets of counts, right? And ChatGPT gave me this, which I don't think it really does the job. I mean, it's beautiful and it's interesting to look at, but yeah, it's not quite there yet. So, well, we'll see how it does next year. All right, so let's stop and do a little concept check. Let's say that we have age measured in a population. And unlike our population that we were looking at where we had just preschoolers, now let's say this is a general population, age takes values between 0 and 100. Let's say I don't have the whole population data set, but I have already computed the density for this population, and I know that the density is this. So what I mean by this is that for any value little x, the value of the density is just what happens when I plug in little x here. And I compute this. So for example, if I put x equals 10, then the f of 10 is going to be equal to 100 minus 10, 90 over 5, 0, 5, 0. So age takes these integer values. So another way you could think of it, instead of as kind of a mapping, you could imagine again the table. Or you have x, there's f of x, 1, 2, all the way up to 100, and then you have the density values here. Okay, so my question is that if this is the density, so you could literally just fill in each of these values by computing it if you wanted, or I could just write it as a formula, which effectively just tells you how to fill in such a table if you wanted to. But obviously this is much more compact than having the whole table. So question for you is, if this is the density, what's the probability that somebody is exactly 0 years old? They haven't turned 1 yet. And what's the probability that somebody is between 0 and 5 years old? Okay, so the first one is easy because I basically already just showed you how to do that. I'm just asking about the case where x is 0. So I'm just telling you compute f of 0. And that is exactly 100 over that. So if you want to simplify it, you can, 10 over 505, right? That's, or you can divide that by 5. It's 2 over 101, I think, as well. Okay, so yeah, roughly one out of 50 people hasn't turned 1 yet in this population, is what that says. Now the question is, what's the probability that somebody is between 0 and 5 years old, inclusive? That's also quite simple. We just have to, if we were to write this way, it's what's the probability that x is 0, 1, 2, ... 5, or the probability that write it this way as well, just alternative notations. So those things are equal, and we know that to calculate that, we just have to sum up from starting at x equals 0 all the way up to 5. So this is another notation. This is a kind of specialized notation for when the thing that the set that you're looping over is integer values, and you're starting at a particular value and ending at a particular value. Sometimes you could also write that as, x in 1, 2, ... 5, right? This is the kind of more generic way, where, because sometimes, like if I were taking all even numbers, right, it wouldn't just be 1, 2, 3, right? I would skip. I would go 2, 4, 6, 8. So this notation doesn't really work for that. But so this is the more generic notation. This is the more specialized notation that people use when you're just going from 0 to 5, every single integer. Anyways, we know that all we're doing is adding up the values of the density at each of these inputs. So concretely, that's going to be, well, the first one is that 2 over 101, and then the second one is going to be 99. Why? Because it's 100 minus 1. 50. And then plus 98. 50, 50. Plus 97. So 0, 0, 1, 2, 3. So you get the idea. And then the last one, which corresponds to 5. Right? And since we're always dividing here by 50-50, if you want to write it kind of more compactly, you'll see that this is just 100 plus 99, 98. Right. So fine, whatever. You can just add these together and divide, and you'll see you'll get a some number out, and that's it. Another problem. Let's say that you have a variable x and it has three possible values, 1, 2, and 3, in the population. Those are the only values it takes. Somebody comes to you and says, the density function for this variable looks like this. At the value x equals 1, the density is -1. At the value x equals 2, the density is 1. And at the value x equals 3, the density is also 1. So the question is, conceptually, why is that impossible? So there's a couple of things going on here. The first is that the density at the value 1 is a negative number. Why can't that be the case? Well, the density is just, for a discrete value, is just the proportion of times that something happens in the population, that x takes that value. It's not possible that a proportion is a negative number, right? You can't have a thing happening in negative 100% of the people, which is what this says. So it's just an absolutely nonsensical value. So that's number one. The next thing is that, like, let's say that weren't the case. Let's say that value were 0, so that would be fine. But just looking at f of 2 and f of 3, both of those are 1. What does that tell you? That tells you that x takes the value 2 100% of the time. But then you also have that x takes the value 3 100% of the time. And that can't be the case. So, because either the value x is 2 or it's 3, right? So this is also nonsensical. So overall, this PDF doesn't make any sense. And in fact, those two observations are actually kind of concrete instantiations of general qualities of a PDF, which is that a PDF, for any value, has to be positive. And then the other thing is that they have the PDF summed up over all the values has to be 1. So I'll just put your script x. Those are all the possible values in this case. Has to sum to 1. Okay. Because this is essentially you're adding up the proportion of time that x takes every possible value. So you're kind of asking in what proportion of people does x take any of its possible values, and that always has to be 1, right? And you basically the population has to be divided. If you look at this example here. If you look at this example here where we had this population data set and we made the density for it, you'll notice these numbers sum to 1, right? You've actually, because if somebody is in this bucket, if somebody has age 1, they're not in any of these buckets. So you've basically taken the whole population and you bucket it into 1-year-olds, 2-year-olds, 3-year-olds, 4-year-olds, 5-year-olds. How many people are in the total? It's however many people are in the total population. So it's just kind of like a bucketing scheme. All right, so these are some general rules that, again, you will see kind of presented in more mathematical treatments, but the conceptual thing is what is really important to understand. So let's look at the next problem here. Let's say that a variable x takes integer values between a and b, and it has some PDF f. Here I'm asking, what is f of a plus f of a plus 1 plus blah, 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 up to f of b? And how do we know this without even knowing what the density is and what a and b are? So some of you may recognize that this is exactly this up here, right? If my set of possible values are all the integers between a and b, so we're starting at little x equals a and going up to b, this sum is exactly this sum of all the possible values of the density, which I've just told you, has to be exactly 1 for the same reason that we discussed above. So that is how you These problems are not practical. Again, this is not a thing that you're going to have to do in a data analysis. That's not the point. The point is that we're understanding some fundamental concepts without which we will be completely unable to understand the required assumptions and implications of the kind of data analyses that we will end up doing.